Looks like we are live. Alright. Not sure if you can hear me. Alright. There we go. So I was just looking at the research paper for this. And I'm gonna be trying to work this out today. Let's try to get the libraries done. I'll include everything in this once it's done in the test classes. It's in here. This was when I tested the which one was it? Yeah, CME Sphinx. It seems to work, but it's not. It doesn't work too well. You know, I think I can show it to you right now. Let me run it. New live search. Previous cache data. Get result print yes. Okay. So let it load and I'll say something from the grammar. So if I say you pause. Thing is working or not. It keeps breaking sometimes. You pause. Never mind, I guess it's broken. It's still broken. It's always fun to see things like this break every time, you know. What is going on here again? Okay, this was when I helped out friends. Let's just delete that really quickly. Okay. Alright. It's over here. I have written a few things that I need to do. So I don't know, I did something. Let's just go ahead and get the Gradle down for this, maybe. Extra tutorials. I should probably also be recording this up. So there you go. I'm gonna record it. Let's go ahead and get quick start. I believe if I scroll down here, I don't want to wait for source actually. Backends, yeah, backends. Oh no, wait. We shall go here to. Yeah, all these things appear. CPU for backend. I do not wish to use CUDA right now. I don't have a proper graphics processor, so let's quickly get the backend for the CPU. We want Gradle Core. This is the one that we want. We do wish to get that as well. So let's head out here. Build a Gradle in the 4J machine learning. Go ahead and drop that in there, and go ahead and drop this in there as well. Hit refresh and we wait for this to download. It's quite a steady upload speed. It does drop in the middle a bit, but that's fine, I guess. We have one concurrent viewer. That's likely me. Life. Let's wait for this to happen. While that's happening, let's go ahead and take a look at what Baidu's paper has when it says the convolution networks really quickly. Pico shows the wireframe of architecture and lays out swappable components. We explore in detail. Convolutional input layers followed by multiple recurrent or one fully connected layer before the softmax layer. So let's fire up one node and see what that actually. Go ahead and just a quick node trace quickly. New page. Actually, let's do it in video here really quickly. New page with cause page right? Okay, so model architectures. The recurrent neural network And so if we look at it properly, we have 1 or 2D. Okay, what are these? 2D invariant convolutional networks. Let's see if I get these. Oh, it's like really early in the morning, so I'm like kind of sleepy. So let's see. Right. Emphasizing edges. Actually, what's an invariant convolution then? Oh, okay, so basically it just sees that it doesn't matter where it is, it's just there, right? So it's got three convolutional layers which are invariant. So what we can try and do is head over to the deep learning thing and see if they have anything on translational layers for convolutional networks. So we're gonna do it and translate the program. Alright, let's take a look. FaceNet is difficult. What is FaceNet? Is it okay, so basically ImageNet, that is a bit used to take a look at your face, alright? What's funny is that deep learning is written in C++ as well. I guess not because I didn't bother to read these, but we continue to create a model of handwriting recognition over years, accuracy of over 9. Nice. Although it's not what we're gonna be doing today. Can we just head over to the convolutional networks really quickly? Convolutional networks. Oh, okay, right. Using central loss. There's so many new terms, I swear to God. Velocity and distance. Measure similarity between two non-zero vectors of an inner product. What's an inner product space? Hausdorff-Pre-Hilbert space, the vector space with a binary operation called an inner product. doesn't really explain what an inner space is. What is inner product space? Ah, okay, that makes way more sense. That makes way more sense. Okay. Alright. Between the two. Alright, okay. Where is the cosine of the angle between them? Cosine of 0 is 1 and any angle, and it is less than 1 for any angle in the 0, 1 radians. Right. Orientation and not magnitude since it's measuring angle, right? Two vectors oriented in 90 degrees relative to each other have a similarity of 0. Two vectors diametrically opposed to having a similarity of -1 independent of their magnitude. Why, when cosine simulate... Alright, here we go. Let's take a look. Three vectors as illustrated in figure 1. Where is figure 1? Okay, is this figure 1? Let's go ahead and open it in a new tab and put it to the side so we can refer to it at the same time. Right, so OA, you know what, I'm just gonna copy that image, put that in there. Oh god, okay. Oh jeez, it's kind of hard to see. Please leave for 3 seconds. That's fine though. Let's pick up the drawing tool. We have from OA, OB, and OC, right? OA, OB, OC. OC is here actually. I think a better place to put the image would be here. Okay, just... that's weird. Don't say so. Points A, B, and C form an equilateral triangle. This means the Euclidean distance of these points are the same. In this case, the Euclidean distance will not be effective in deciding which of the three vectors are similar to each other. Although the magnitude length of the vectors is different, cosine similarity measure shows that OA is more similar to OB than to OC. Now, why is this? Because if you look... Oh, okay. As you can see, the cosine similarity measure is better than Euclidean distance versus the OB and closer to each other. Since the values are way smaller compared to OA to OC. Okay, they're cool in here and it's illustrated. So if they're all similar, as in like this, then you can't really use cosine similarity because there is no angle there. So then you can simply just get a Euclidean distance to figure out that B to C is... oh no wait, A to B is the closest because it's the smallest number. Nice, actually. It's very nice. Alright. So, is no longer required. In addition, because hardware is better utilized, the amount of time it takes to train embeddings is much shorter. One important distinction when it comes to central loss versus a triplet loss architecture is that a central loss layer stores its own parameters. These parameters calculate the interclass center of all examples for each label. Deploying for J, you learn how to train embeddings for facial recognition and transfer parameters to a new network that uses the embeddings for feed forward. We'll be using a computation graph via the open phase and enforcement variant, which is a hand-tuned parameter minimized model of face net. That is quite the amount of imports. I will let IntelliJ handle those. Alright, so now it goes straight to the stuff here. Let's take a look at what they've done. Jesus Christ, alright. Oh, okay. Virgin, alrighty. Or should I? Okay. Never mind, I guess. Or should I? Huh. Didn't know I could set it up like that. But there's no point in setting up a camera like this right now. Close that really quickly. Pick up whatever I've dropped because I don't want it staying there. Stay. Okay, I'm back. Alright, so okay, taking a look at this very quickly. So random seed is 1, 2, 3, because why not? Iteration is almost always 1, okay. Transfer function, activation of value, shape array of integer, alright. Is it done in C++ or something? Or Python? Not sure. Oh, it looks like Python. Actually, never mind. What's up with the random semicolons? Doesn't matter, does it now? Is equal to this? No, it's very clearly Java. Neural network configuration dot builder seed activation dot identity, which was actually relu, I believe. Actually, no. What is identity? What is the identity activation function? What, why, which are? Let's take a look at it. Hmm. Is the input signal proportional to the input? Okay. Wonder why we're doing that here. I have your gradient descent. You have your new updater as an item. What is really needed this updater? Okay. That's quite a few updaters, jeez. Let's take a look at all of them. Okay, so this is the most common, or like the simplest one of them. Of Adam and beyond. Alright, here we go. This is there's so much to learn. We need to say a little more. Okay, this is an entire overview of all of them, I believe. Oh, this is nice actually. Oh, these were literally just programs. Seems legit. Alright, let's go through this. To reach a value, alright. So basically, if you guys remember the mountain example where you're trying to go down to the bottom, that's basically what it's saying. It tries to pull the thing down to the bottom where the mistake or the cost is the lowest, yeah. The three invariants for gradient defense, whichever and how much data we use to compute the gradient of the objective function, depending on the amount of data, we can make trade-off between the accuracy of the parameter update and the time it takes to perform an update. When the gradient descent, aka batch descent gradient, computes the gradient of the cost function WRT to the parameters theta for the entire training data set. For I in range NB underscore epochs, so the amount of epochs I believe. I don't believe we can use this because since I would love to again do this, but at the same time training would be difficult for an ASR on the fly. I would like to implement that though. It would be a very nice thing. So parameters so good. Evaluate gradient. Okay, so we're gonna. Alright. Let's see future. Okay. Good idea. Okay. Learning it. Not a way to that. There's quite a few things here that I. Okay. Jeez. Wait. These things there's so many things here that I have no clue what's going on. But it is referring to a graph. But at the same time, it is in neural net config. Jesus Christ. There is quite a few there. Okay. Alright. That does really break your head quite a bit. What's an acyclic graph? Having no graph cycles. Oh my goodness. Alright. Alright. Alright, so let's start with the very basics, shall we? We have a multi-layer configuration with seed with an update of we're using Nestorov's updater. Okay. I wonder why we're doing that. But let's say we are. Okay. Okay. So you have to put an output layer at the end. Do you have to put an input layer anywhere though? Weird. High level configuration. Update algorithm. There's Nestorov's momentum. Alright, okay, so okay, that makes more sense. If I actually put this in IntelliJ, I believe I should be able to take a look at what they actually mean. So let's try that. Is val a thing in my thing? Okay, not. What was the thing? It was Lombok? No. It is Lombok, right? Alright, it's firstly find local variables. This is required. Yeah, I believe it is. Super nice. Let's go ahead and look for Gradle. So Maven Central, and we shall kidding. Do we need version? I'm not sure if we need it, so I will include it in my build.gradle. Is change this to wait, what is compile only? Exactly. Compile assembly versus implementation. Let's stick with implementation. Implementation, and hit rebuild. Should really quickly do this. There we go. File should be available. Go ahead and import that. We have a multi our config is equal to new multi there configuration dot let's take a look at it again. Neural net. Okay. So we have multi-layer configuration. Okay, wait. What's going on here? Sad. Get filter dot. Alright, and now everything comes up. Seed. Jesus Christ. Okay. I wonder how this works. Alright, updating. Oh, okay, interesting. Newness. Oh, okay. Learning rate. Okay, it's looks like it's changed. Nope. So he has the momentum set to 0.9. Let's just go with what they have. And then I believe they just did a list. And then they added. Oh, is it inside the list? Nope. Oh, there. And that's what they're doing here. New. And then they keep adding the layers. So let's add a layer really quickly. Add position 0. Index 0. Let's add a new dense layer. Data dot end in, I believe. We'll have one input. Okay, we have apparently 784 inputs. Dot end out. That's 100, I believe. I'll set that in a second. Waiting it will be written into our savior. So wait. Calculation as your calculation as value and dot build. Alright, dot build semicolon and out as 100. Let's take a look at Nesterov's algorithms. Okay, it's literally learning code. seems legit. I updated. Alright, here we go. Interesting. Ooh. Okay. So, wait, does it really matter? Oh. What is this really? How does the initial? Oh, okay. Been streaming for quite a while now. It's been an hour. Let's go for 10 more minutes and then we'll stop for the first day. This is related to a simple one-layer network with no activations. Each layer is a matrix A that contains layers and weights. In order to complete a single forward pass, we have to perform a matrix multiplication between the inputs and weights at each of the 100 layers, giving for a grand total of 100 consecutive matrix multiplications. It turns out that initializing values of weights from the same standard normal distribution to which we scale our inputs is never a good idea. Okay. Why is it so? We can simulate a forward pass through a hypothetical network. Okay. Oh, okay. Ah. Completely vanished. Jesus Christ. And if you have an output y that is the product of a matrix multiplication between x. Where I is row index of function A, K is both, okay. You know what? It's 7:45 and I should probably go get ready. So I'm gonna end the stream here. I'll be archiving this so it won't really be live, and also recorded it. So if I'm gonna, so it's just as a track of what I could do right now. So I'm gonna be stopping the stream right now, and I guess I'll be streaming again tomorrow or later today, doing the exact same thing, and let's hope we make more progress later on. Learned quite a bit of things today, but I'm gonna end it right now. End stream, and we'll no longer be live.